Today's talk is going to be given by Jacob Hodis. He is the head of research department at Nokia Bell Labs in France, and focusing on radio systems and artificial intelligence. Prior to this, he was the co-founder and CTO of a social network Sprite and worked for Alcatel-Lucent Bell Labs in Germany. He received the diploma degree in electrical engineering and information technology from RWTH Aachen University, Germany, and the PhD from Superlake Gif-Serviet in France. His research interests are in the areas of machine learning, cloud computing, SDR, large random matrix theory, information theory, signal processing, and their applications to wireless communications. He is a recipient of several prizes and awards, which includes the Nokia France Top Inventor Awards. I have just summarized the prizes because there are several. In today's talk, Jacob will will describe the idea and the road towards a possible 6G system, which is designed in a way that machine learning is given the opportunity to design the path of the physical and medium access layer itself. So I would like to welcome Jacob. Good afternoon and welcome to the webinar today. Thank you so much for joining, and the floor is yours.
Yeah, so thanks for the introduction, and thank you very much for inviting me to give this talk. There's not much to say to introduce myself because you have said it all. Maybe just a precision. So what we do in our research department is to explore the use of machine learning for the physical and MEC layer. And today I would like to present our vision of a possible AI native interface that might play a role for 6G and a possible road towards it. So let me start by quickly painting a vision of how communications could look like in 2030 and what 6G might be used for. We can think in terms of three major categories here. So the first category is about creating and consuming new virtual or digital twin worlds. An example use cases for this would be mixed reality telepresence, so almost like the Star Trek holodeck for the Star Trek fans in the audience, high resolution mapping, which is needed for the creation of digital twin worlds, or simply enabling designers to mix real and imaginary objects to see what the designs would look like. The second category is about augmenting our intelligence. So far, we actually use our networks only to get access to information. So if you do not know something, we look it up through a search engine. But as artificial intelligence becomes more powerful and widespread, we will look to machines to provide us with intelligence and not just information. We can also learn a lot about ourselves through body sensors, and network-based monitoring and analytics can make security lines a thing of the past, for example. Now, the last category is about controlling our automatons or robots. And I think it's clear that we will see many more of them in the future and that they will all be network orchestrated. And the way I see the role of 6G is to enable this new lifestyle at a global scale. So what I've been talking about so far is really the unification of our experience across the physical, the digital, and the biological worlds. And we need several new emerging technologies to achieve that, and which in turn will drive new connectivity solutions. So for example, we need new sensing and actuation technologies to create the digital world and also manipulate the physical world from within the digital world. The computing requirements for this will increase enormously, and distributed computing will be a major new theme. Our devices may not be able to meet all of the compute needs and will rely on a combination of edge cloud and local near device computing. And we will also need knowledge systems that will store and process data and perform reasoning, prediction, and planning. And lastly, the creation of digital worlds will require new ways of providing information to the humans through human-machine interfaces, for example. And the role of 6G will not only be to provide the connectivity for this, but also to maintain synchronizations across these three systems to create a truly holistic experience. So we currently see 6 key technologies that are needed to fulfill the 6G vision. The first is the air interface framework, which will most likely be designed so that it can be optimized and customized using AI or machine learning techniques. We will expand the use of spectrum to higher bands beyond where we ended up with 5G. Equally important will be new ways for spectrum sharing in the sub-3 gigahertz bands, where it will be harder and harder to find sufficient spectrum for the ever-increasing data rates. We will design our systems for simultaneous communication and sensing, or maybe even other services. And this bears a question of how can we use the resources of sensing devices. It means we need to invent new scheduling algorithms that meet new requirements. And we also have to invent new ways of multiplexing waveforms, which are needed for each type of service. We must further evolve the architecture for increased flexibility and specialization that is needed to meet the need of new verticals. And as the core gets further distributed and the RAN becomes more centralized, there's actually an opportunity to converge some of the functions to a further lower cost. The URLLC service that begins in 5G will be further refined and improved in 6G to meet even more extreme requirements. And finally, we need a new security and trust paradigm for when we start sharing entire digital worlds with others. We must guard against inadvertently sharing information with others, and also jamming of private networks is a potential problem that needs to be addressed. So, of course, all of these topics are very interesting and important, and we could have a talk on each of them. I will focus in this talk on the AI interface, because this is what I'm mainly concerned with in my day-to-day job. Let us start first with having a look at the role of machine learning for 5G. There are essentially three reasons to use machine learning, which are an algorithm deficit, a model deficit, or simply prohibitive complexity of alternative solutions. Today, machine learning starts to be used throughout the 5G RAN on all layers, and I have simply listed here a few use cases to which I have been exposed to in the past, but there are, of course, many more. Now, I think it's fair to say that machine learning is only used to implement 5G, but there's not a single component of 5G that has been designed by machine learning. And this brings us to the central question, which many researchers ask themselves at the moment, which is what if 6G was built in a way that machine learning could optimize parts of the physical and MEC layer if needed? Now, let me walk you through some possible benefits of such an approach. So first of all, one could learn bespoke waveforms, constellations, pilot signals, and so on, that make more efficient use of the available spectrum. Second, on the MEC layer, one could learn custom signaling and access schemes, which could, for example, seamlessly switch between contention-based or scheduled access if needed. Third, a learned air interface could embrace hardware nonlinearities and limitations and fully adapt to them, whatever the target platform is. Fourth, the current 5G physical layer is full of options and parameters that no human can optimally set, and it would be quite desirable to get rid of many of these and let AI figure out what to do. Fifth, having less options which needed to be implemented and not having to design custom implementations for each hardware platform would allow for drastically reduced development and deployment times. And lastly, an AI-defined air interface could lead to reduced standardization effort in the long run, because we would only need to standardize procedures and signaling that enable self-learning. Let me now provide another view that explains the potential rule and scope of an AI-native air interface. So one key difference in the design process with respect to traditional approaches is that the air interface could not only be optimized to reliably transport bit streams, but rather to serve an application with the data it needs in the most optimal way. And this means that the way data is communicated depends, of course, on the data itself, the hardware of the communications devices, the radio environment, and the application which is consuming the data. And this is a quite significant shift away from the classic Shannon theory. So in other words, the air interface would learn to communicate only relevant information for a specific task. And this is a highly desirable feature as networks get more and more specialized. And 6G with an AI native air interface could emerge bespoke communication schemes for each and every application, hardware, and environment. Now, of course, developing such a system does not happen overnight, and it's important to have, I think, to have concrete steps and milestones towards this ultimate goal. And I currently see 3 important phases which we will need to go through before we can truly deploy an AI native air interface. In the first step, and I think this is what's happening right now in the industry, we will use machine learning to enhance or replace individual processing blocks, mostly in the receiver. And examples could be, for example, a branch detection, a MIMO detection, channel estimation, etc. In a second step, we will try to aggregate multiple processing blocks into a single machine learning model. And this means that more trust is given to ML, since it is less understandable what's happening, but also the potential gains are higher. And in a third step, we will give even more freedom to AI and let it design parts of the physical layer itself. And this could be, for example, new modulation and piloting schemes, but maybe even new waveforms. Let me now explain why each of the steps is necessary. So already this first step where you replace a single processing block by a machine learning model, such as a neural network, it's actually a paradigm change in the way the industry designs and deploys radio transceivers. So one needs to solve issues such as online training, as well as fast adaptations through transfer learning and federated learning if you want to retrain machine components in the UE side. The positive aspect is that no new signaling with respect to 5G is required to implement this. The second step is crucial in my eyes, because this is where we'll see for the first time significant benefits of machine learning. I will show you an example later on. So as the neural networks we use will grow larger, hardware acceleration becomes increasingly important. And vendors also need to commit to a machine learning only or machine learning first approach, because it's simply not viable to develop machine learning or non-machine learning backup solutions in parallel. And then the third step represents, again, another paradigm change in the way communication systems are designed, because not all of the aspects of the physical layer are fixed in advance. And this approach requires entirely new forms of signaling and procedures to enable distributed end-to-end training. And this is something nobody has ever done before. So as you might have noticed, I'm becoming increasingly technical in my talk, and I wanted to comment on this debate between data-driven versus model-based approaches. I think that both worlds can be very easily combined thanks to fully differentiable transceiver algorithms. So take, for example, here a typical chain of receiver algorithms: synchronization, channel estimation, equalization, symbol demapping, and decoding, in which you would like to replace or enhance a single block with machine learning, such as channel estimation. So you could replace, for example, the LMMSE matrix, which requires the knowledge of the second-order channel statistics, by the output of a neural network that would only get the SNR as an input. And now, if the entire receiver here is differentiable, we could train this neural network with respect to a loss, which is defined as the receiver output. And the advantage of such an approach is that we don't need block-wise ground truths for training, and each block is optimized for the end-to-end performance rather than individual metrics, which are only vaguely related. So in our toy example, the channel estimator can be learned without access to actual channel realizations. And that's in practice, that's something you do not have. Now let me speak a bit more about this end-to-end loss. So I would like to describe one loss, which I think is quite universal for communication systems, because it has a very strong information theoretic, but also practical motivation. And to make it very simple, we focus on a single transmitter communicating with a single receiver over a channel. The input is a vector of m bits, and the output of the receiver are estimated posterior probabilities of the individual bits. This is p tilde of bi given y. Now, from a machine learning perspective, a typical training loss would simply be the sum of the binary cross entropies at the output of the receiver. Now, it turns out that this loss is actually perfectly adapted to communication systems because we can rewrite it in the following way. So the first term, M, this relates simply to the number of transmitted bits or the entropy of our data source. The second term, this is the sum of the bitwise mutual information, which is also called the bit metric decoding rate. And this depends only on the transmitter and the channel. So it depends on Y, so what comes out of the channel, and the bits that are fed into it. So it only depends on what the transmitter actually does. And now the third term we have, this is actually the loss in rate that we have because our actual receiver, so which is in my image here noted by G of theta R, can only produce estimates of the actual posterior bit probabilities. And so this loss is the Kullback-Leibler divergence between the ideal kind of receiver and the receiver that we have learned. And now this term in the parentheses, this is actually a rate which is achievable with a mismatched bit metric decoder. So for example, we would now use the estimated posterior bit probabilities to feed a belief propagation decoder for some LDPC code. So this is actually directly related to the bit error rate you would see. So this means that minimizing the binary cross entropy at the output of this receiver means actually to maximize an achievable rate with a practical decoder. Now I'd like to visualize this with a very nice video, which is courtesy of Sebastian Dörner, who's a PhD student at the University of Stuttgart. And so what you can see here, there are many things going on. So I will walk you through this, and then I will start a video that actually shows how the system is learning. So in the top left corner, you see the constellation, which is used to modulate the bits by the transmitter. In this case here, so we have 16 possible messages, so 4 bits, and we communicate over a very simple AWGN channel. And so this constellation is actually what determines the bit metric decoding rate. So we'll go back here. So this determines this first term in dark blue. Then we see on the bottom right, we see 4 plots, which shows the decision regions for each of the 4 bits. And this is actually something which is learned. And so this means the closer to the true posterior probabilities these decision regions actually converge to, the better it is. And this actually, so the better we train, the smaller the loss actually in our achievable rate is. Now on the top right corner, you see a plot that shows achievable rates of various schemes with respect to the signal to noise ratio. I will already start a video. Hope it will play. Yeah. So actually everything was initialized randomly here. And now you see as the training progresses. You see at the bottom, you actually see the number of training iterations, the batch size, etc. Let me now stop, for example, here. So what we can see in the top right plot is you have the Shannon capacity in blue. Then you have in purple the bitwise mutual information that you would get using 16 QAM and an ideal receiver. Then you have the essentially the bit metric rate that you get when you use the currently learned constellation together with the optimum map detector. Then you have this other curve in orange, which is actually our end-to-end learned system. And for the moment, you see, for example, that we have actually we're doing worse than all of the other schemes because the training hasn't really progressed much. But as the training continues, we will improve. I also want to highlight that we train here for a very specific SNR of 3.85 dB. And our goal is now to actually become better than the 16 QAM bitwise mutual information baseline. Okay. Training continue. So you can see, for example, right now, our system has only learned to come up with a constellation that looks like 8 PSK. and we are able to actually separate only 3 bits of information correctly. Now you will see as training progresses, our constellation will be optimized in a way that we can actually clearly separate 4 bits. At some point, actually, you can see now that's the gain. So now the gain is green. So now we beat the 16 quantum baseline. And also the decision regions start to stabilize. At some point, we actually have converged. And so the nice thing is that by doing this training approach, we get the optimal constellation, which is optimized for one target SNR together with the associated bit labeling. And we slightly outperform 16 quam constellation, and also our detector has actually converged to the maximum likelihood detector. So this means it cannot do any better than that. So now the goal is, of course, to use this idea for more complicated channels and not just an AWGN channel. And I would now like to speak exactly about this, about a case study, which ranges from neural receivers to pilotless transmissions, where I try to show you examples within each of the 3 steps towards the AI native air interface that I've explained on the previous slides. So let me first set the stage. So we focus on a single input, single output, so a SISO, a doubly selective channel. And we use OFDM, and the unit of interest for us is a transmission time interval that consists of 14 subsequent OFDM symbols over 72 subcarriers. Now in this grid that you can see, each dark rectangle is 1 resource element, and on some of these resource elements you have pilot tones. Now for this channel, for this system model in the frequency domain, you can represent the matrix of received signals, so size 72 times 14, as the element-wise product of a channel matrix H together with the transmitted symbols plus a matrix of independent Gaussian noise. And now we assume that the vectorized version of H follows a complex Gaussian distribution with 0 mean and a covariance matrix that has a Kronecker structure, so consisting of 2 matrices, RF and RT. So this matrix RF describes the spectral correlation, so across subcarriers. And this depends on the subcarrier spacing, which is 30 kilohertz in our case, the delay spread, which is 100 nanoseconds, and a power delay profile, which I've chosen to be the TDLA power delay profile. The temporal correlation is described by this matrix RT, which is actually the Clark's-Jakes model, which depends on our carrier frequency, which is 3.5 gigahertz, and the speed of the transmitter, which is 50 kilometers per hour. And our baseline system, so which is not learned, will use a 60 QAM modulation and a 5G code with a block length of 1024 and a rate of 2/3. So this is our system and channel model. Now we have a baseline system against which we will benchmark everything that machine learning can do. And this is actually a very practical baseline receiver, which you can find in minor variations in many products that are running throughout the world. So we assume that we do least squares channel estimation at the pilot positions. So see on the top right corner, you see essentially in blue, this is where the pilots are. And you make a least squares channel estimate at this position. And then you equalize a resource element using the channel estimate at the nearest pilot position. It means, for example, for this, all of the resource elements that are marked in red will use the top left blue least squares channel estimate. Then the symbol demapper, which computes log likelihood ratios. This block assumes actually a Gaussian post-equalized channel, so with a known variance. And for decoding, we use a textbook, sum product, belief propagation decoder with 40 iterations. Now, this is just a plot to show you the difference between a perfect kind of channel state information based upper bound on the performance versus our baseline receiver, the bit error rate versus SNR. And there's roughly a room for 3 dB improvement. So whatever we do with machine learning, we are somewhere in between this range, And now I would like to look at why do we actually see this performance gap? And there are multiple reasons for this. So if you look at, so here I've just shown you, so you see 4 subcarriers and 14 adjacent OFDM symbols. And in purple, you see the transmitted 64 QAM constellation. And in this light blue, you can see the equalized received symbols. And this is at an infinite SNR. So what you see is only the effects of the channel. And what you can see is that so close to where the pilots are, so this is where you just see a single dot. So this is in the 3rd and the 12th OFDM symbol. So close to where you have the channel estimate, this equalization is very good. But if you move away from it, for example, towards the center of our grid, so at OFDM symbol 7, due to channel aging, actually the equalized constellation drifts away. And this is where the demapper actually will make huge mistakes in computing the LLRs. And this rotation has also the effect that the SNR, you can see, degrades. So we have mismatched LLR computation and SNR degradation because of, one hand, imperfect channel estimation and also channel aging. And so if you could get rid of these two aspects, so have a better channel estimate and combat channel aging, you would possibly get much closer to the perfect CSI baseline. And I would like to present you several increasingly complex ways to do this. So the first one is what I call a symbol-wise neural demapper. So it means this demapper is a small neural network, an MLP, which looks at every equalized symbol one by one. So it gets essentially the real and imaginary part of X hat ij as input, together with an estimate of the SNR from the equalizer. And we also give it a positional encoding of the position, so within the grid, so of the coordinates I and j. So it's just another representation of where you are looking. And so this means that this neural network can actually learn a grid position dependent demapper. And this should possibly help us to get better LLRs. So when we just go back, you can imagine that, for example, in the 7th OFDM symbol, the way that you should compute LLRs should be very different from how you compute it close to the pilots. And now here, this gives us some, but only meager performance improvements. And the question is, what can we do better? Now there's, I think, a quite nice way of doing this, is to have actually the demapper to look not only at a single element at a time, but at the entire resource grid. So we will now feed the demapper with a tensor, so which contains the real and the imaginary parts of the equalized symbols, together with the SNR for each of these symbols. So it's a tensor of size 72 times 14 times 3. And this neural network will output directly the log likelihood ratios for all of the resource elements. So for each resource elements, we get 6-bit, or essentially six outputs, and where each output corresponds to the LLR for each of the bits. And the nice thing is that this gives us actually quite substantial gains. So you can see that we gain here more than 1 dB over the symbol-wise demapper. And the reason why it can work so well is that it can actually use the pilots together with the data symbols to compensate for channel aging and the mismatched LLR computation. So maybe I go back to this thing here. So if you look at this plot, I think you could imagine that you would be able, by looking at it, to figure out how you would need to scale and rotate each of the resource elements to actually come back to what it should be. Now, of course, you only in practice, your neural network actually sees for each resource element only a single symbol. But if this observation window is large enough, it can still detect statistically how it should actually backrotate things. And but in order to be able to do so, you need actually to have the right neural network architecture, which allows you to do this. And so this is really key. And this is inspired by work of some of my colleagues. So key authors Mikko Honkala, Jan Hutun, and Dani Korpi, who have published a quite nice paper called DeeperX, where they leverage a fully convolutional neural network architecture for receiver purposes. And so fully convolutional means that every layer in your receiver architecture is only convolutional. And you have these skip connections between every few layers, so which allows you to actually train quite deep architectures. And another key component is the use of dilated convolutions. So in a non-dilated convolution, so you would, for example, have a 3x3 filter. This is what you can see here in the top image on the right. So it's a 3x3 thing that you would swipe over your input channels. And if you dilate it, you essentially, this is as if you had a filter of size 7x7, but it would be filled with zeros apart from 9 positions. And by doing this, actually, you increase the receptive field. So this means the number of inputs which are actually impacting one element of your feature map at the output of the convolutional layer. And by increasing gradually the dilatation of these convolutions, you can actually achieve a neural network that has the output that every output element sees the entire input with a reasonable complexity. And so this is very important for our problem here, because ideally we would like that, the LLRs that you estimate for one resource element are able to make use of all of the data you have received over the entire grid to figure actually out how the channel has deformed the original constellation. Now, there's one more thing you can do, and this is now going towards step number 2 in what I've described in this way towards an AI native interface. You can actually not just replace a single component, but maybe even multiple components. And now what I've done here, I've used the same neural network architecture, which was used just for this gridwise demapper, but let it also do the task of channel estimation and equalization. So essentially, this neural network here gets only the post-FFT resource grid. So this is now a tensor of size 72 times 14 times 2. And again, it outputs the LLRs for each bit and each resource elements. And you can see that you gain again half a dB with respect to this gridwise neural demapper. And now we start to be fairly close to the perfect CSI baseline. And it turns out that if you make the resource grid that you feed into the deep receiver larger, you can get closer and closer and closer to the perfect CSI baseline. And so this is because this receiver can really do data-aided channel estimation, equalization, and demapping. And now I would like to come to the third step by looking into what could we actually do better if the transmitter was given more degrees of freedom. And so what I've done for this case study, for this talk, I have now kept the same neural receiver as for this blue line, and now had the transmitter optimize the constellation, which is used to modulate bits. So this is essentially a tensor of size 64 times 2, because we have 64 possible constellation points, and each of them is a complex number. And I have actually so scaled this constellation so that it has in total unit energy and also zero mean. So it means this constellation cannot contain a superimposed pilot or anything like this. Okay. And now I optimize jointly this constellation together with this deep receiver. And so what you can see is that we get essentially the same performance in terms of bit error rate, as the 64 QAM system with a neural network-based receiver. But the huge difference is that we don't use pilots at all anymore. So this means this constellation that I've learned is used across the entire grid. So there are no pilot tones at all anymore. And you still get the same bit array performance. And this means that you get actually a around 7% increased throughput. And also you do not have the headache of managing where to place pilots and so on. And just to give the teaser of how does such a learned constellation look like. So here you can see these 64 points. And this constellation has only a single symmetry axis. And this means if you rotate it, you can always actually figure out what has been the rotation angle. And this is something which is not possible, for example, with the QAM constellations. And I've also zoomed into the bit labels. So I've selected 2 rectangular areas where you can see what type of bit labels are learned. And you can see that it has essentially learned a gray labeling. So for example, in the top left corner, you see the all 0 kind of constellation point. And if you look at the neighboring points, they only differ in a single bit. And this is essentially happen everywhere. And now, but the question is now, how could such a thing be standardized? Would you standardize actually learned constellation or just the procedures to actually make system learn such a thing over the air? But time will tell how this could be done. And I would like to conclude this section with a few important research topics that I see for this idea of end-to-end learning. So rather than optimizing just constellations, one can actually easily extend this to emerge entirely new waveforms, which might be relevant for if you look at new spectrum. You can also nicely take into account quite extreme hardware constraints. So for example, low resolution ADCs and DECs. You could impose close to constant envelope constraints, etc. You could also use this now to learn waveforms that are optimized for joint communications plus X, where X would be, for example, sensing. It would allow us to kind of reconsider how we send control messages or packets with only a few bits of information. So one could get rid of this entire preamble, pilot, CRC kind of structure and just learn what would be the most, the most efficient radio signal that you can transmit to communicate 16 bits of information. Then I think it's quite relevant to look into application-specific end-to-end learning. So in my talk, I've looked actually at transmitting bits, but now you could fine-tune this directly for a certain data type, for example, just transmitting images or sensor information, and maybe the goal you want to accomplish is to control a robot. So in this case, one could actually learn the joint source channel coding together with how to interpret sensor data that the actuator decides. Then there's field of semantic communications, where you essentially provide context to the communications. This can also help a lot. And I think the whole field of decentralized and federated learning, especially for end-to-end learning, just starts. So there's a lot of potential, I think, for future research work. And if you would like to put these things into practice, you really need to think about how we can make efficient transfer learning and also meta learning to speed up the learning process. Now I would just like to conclude with essentially a single slide, which I think is the next frontier. So far I have only spoken about end-to-end learning for the physical layer, but one could also think about extending these ideas towards higher layers. So essentially then we speak about protocol learning or emerging new protocols. And so I have just one slide to kind of motivate this. So essentially the way a RAN protocol is done in 3GPP is you have hundreds of people from various companies meeting many times and discussing for many hours, and often with competing commercial interests that impact the way our protocol is designed. And one could think about an alternative to this approach where simply machines could figure out the most efficient form of signaling or channel access with a click of a button. And actually, so the machines figure out how protocols should be done. This is actually a very complicated problem, and I think also the research is just in the infancy. Together with my colleague Alvaro Valcarce, we have started to look into this, but we've barely scratched the surface. So really looked into the problem of, can you learn the channel access policy together with the signaling? Just to be precise here, with signaling is essentially comprises two things. The vocabulary, so essentially, what are the type of messages, the type of control messages that I can exchange? And the policy tells you what is the order in which I should exchange these protocol messages. So this provides essentially meaning to the vocabulary. And then the channel access policy essentially uses the signaling to get the right information it needs at the right time to make a decision on who should transmit when. And so this is a very complicated and interesting machine learning problem. Where, for example, one could look into multi-agent reinforcement learning type of ideas. But I think it could be a very interesting future direction, especially if you think about highly specialized subnetworks. So, for example, learning custom MAC protocols for networks that control how a robot works, or in-body networks for human for sensing of some human human markers, for example. Okay, so with this, I've reached the end of my talk. It'll be 45 minutes, and I would like to thank you all for attending this talk, and I hope that we get some interesting questions.
Thank you very much for the nice talk. Right now, we'll go direct into the Q&A session. So I'd like to invite my colleague Vishnu to moderate the Q&A session. So good evening, Vishnu.
Thanks, Thomas. And thank you, Jacob, for that excellent talk. Let me start off with one which is mine. You discussed about one of the slides you were talking about individual components being designed by ML and multiple processing blocks designed by ML, and then finally the physical layer itself being designed by ML. It looks from this talk that we are at the first level. Is the understanding right? And also you called out the impact to the standards very nicely towards the end, and also in this slide also you were calling out the impact to the standards. So in that respect, question is, which level of this we are at the stage of research today, and what is the current impact to the standards? So of course, you called out the future very nicely, but in the current state of affairs, where are we with respect to the impact to the standards? I'm asking because we have a biased interest because of IT work. Yeah.
Okay, so I think we are roughly somewhere in between stage 1 and 2. So and the reason is simply that in most commercially available products, there are no hardware accelerators for layer 1 machine learning loads. So even if you think, even though most handheld devices now have some neural coprocessor, they are not specialized for physical layer workloads. So that's the reason why it still would be very challenging to replace actually components in the physical layer SOC with neural networks. So I think from what we will see very soon is indeed the use of kind of layer 1, like this level 1, where we kind of applications where some blocks such as channel estimation, for example, could be replaced by neural components. But then it's just a matter of time of giving more space on the silicon for hardware acceleration for neural networks, so that we can see actually the type 2 type of applications. Now with respect to standards, so there's also the reason that essentially step number 1 and 2 have no impact on the standard. So it's transparent. So it means you can do this for 5G at the moment without actually requiring any new forms of signaling. So there you can always essentially get the ground truth you need maybe hijacking a little bit the available signaling that's there. But you wouldn't need to it doesn't, is essentially standard transparent because it just touches the implementation and not, and nothing else of the standard. And so, but as soon as you would like to give the flexibility that, some, really components of the physical layer specifications can be designed on the fly, this means that you would use signaling that actually allows you to enable the training, but also to exchange the related kind of meta information that you need to decode and encode data.
Interesting. Yeah, thank you so much. In fact, that brings us to the next question. When you say exchange this kind of meta information, metadata, would you call that as overhead, or do you think that the savings that you showed, for example, in the pilotless mechanism, how do you weigh these together? Is that the additional information that you pass versus the gains that we get? Is that kind of the gains are better, or would you call that as overhead?
Okay, so this really depends on, I would say the lifetime of a trained model. So this means if you essentially, are training all the time because you can never converge to anything, then it's not worth it. And the training overhead is too high and you don't get any gains. So that's why I'm fairly skeptical about like a per link optimization, because this wouldn't simply scale. So the way I see it is rather you could optimize parts of the physical layer for certain types of channel models, or maybe for a specific cell, which you would use then. And then you essentially would only need to train it once over a sufficiently rich data set, and there wouldn't be any form of online training at all. So for example, what I've done in this case study that I've presented, we have actually trained our system over millions of different channel realizations from this particular channel model. And in the paper that I've showed, and also for my colleagues, they've actually trained a receiver over many different channel models with different speeds, different delay spreads, correlations, etc. And then you test it actually on a totally different channel model, and it still works. So I think there might be for some aspects, this online training might actually not be needed. So, but you could also think about quasi-static networks. So for example, wireless backhaul links, where there is no interference, the channel is quasi-static, you can do whatever you want. There's not even 5G, no standard compliance. And this is, for example, where this idea would really shine, where you could optimize for each link the physical layer in the best way possible.
Interesting. Yeah, thank you so much. Actually, this discussion which we are having just now, it was also reflected in the NCSU challenge, and there we discussed exactly this set of problems of generalization across different types of channels, complex channels, simple channels, and different modeling techniques. So yes, I think it is quite a relevant answer that you explained just now. The next question is in one of these slides, you started talking about data-driven and model-driven. It was quite interesting discussion, but I couldn't conclude it from what you were describing, because yes, we in the talk you were describing the symbol level data, grid level data, but how would you conclude this comment? Is it is the future data driven or model driven? Could you give your thoughts on that?
Yeah, so I think the future is definitely data driven, but it's always important you need to think about how you can inject expert knowledge into a model so that you can train efficiently and also to reduce complexity. So for example, in this, when we look at this in this neural receiver, so that does essentially all of the channel estimation equalization all alone. Here it turned actually out that the complexity is very, very high. And you also, and this is, for example, this is purely data driven. And you actually have no idea what's going on in any of the blocks. And it would be also very difficult to extract now from any of the layers, for example, channel state information. So that's not known. So there's this kind of, what we have seen so far is that often model-based approaches impose some limitations. And for example, especially if you go towards extending this towards MIMO, I think there are many, many papers trying to improve MIMO detection using machine learning. And the typical approach so far has been to kind of inject our model knowledge so that y equals h times x into the neural network. And this hasn't been really successful and also limited performance. And now I think the key to this data-driven approaches is that they allow you to leverage the data and not just the pilots. And you combine both. And this is where I think many model-driven approaches are also extremely complex. And it turns out that purely data-driven approaches do this in a much more efficient way. And so at the moment, actually, I start to believe that purely data-driven approaches will work extremely well in the future, especially if the hardware kind of acceleration brings down the cost and energy consumption of deploying these things in practice. So then I think it could become increasingly relevant. But again, it's so domain specific that sometimes you need a small tweak based on the expert knowledge to make it work, and sometimes you don't.
Yes, understood. Thank you so much for that explanation. I think the next question is about the modulation scheme and its relationship with the loss function. I think you explained, we started off with 16 QAM and then you moved on to 64 QAM. I think that is explained, but could you answer this question? It says that the loss function is tied to parameters of single modulation scheme, which I don't think is true from your talk, but anyways, how can the neural network receiver be trained extended to support wide more communication schemes?
Yeah, okay, I think it's a very good question. And so I think the big problem we have is how can you easily parameterize a neural network? So tell it, now I'm switching to 16 QAM, now I'm switching to this and that. That's indeed difficult to do. Now, first of all, so the first part of the question is with respect to the loss function, how it is actually tied to the constellation. So actually, the loss function is tied to a constellation, to a number of bits that you are transmitting, but these are coded bits. So by the way, so and this means that if you choose this constellation sufficiently large, and you allow the constellation to adapt to the SNR, then you actually you essentially you control very finely how many bits, how many information bits per channel use you can transmit. And this means essentially you can learn a single you have a constellation, for example, of size 256, but if the SNR doesn't support 256 points, for example, half of them will just collapse to the same constellation points, and you would just need to adapt the code rate correspondingly. So this is one way of doing it. You're actually adapting, you have an SNR dependent constellation that just grows and changes things. Now, the other way you can do it is actually you train for specific constellation size. For example, you train a receiver for QPSK 16 QAM, 64 QAM, etc. And you just provide this as an additional input to the receiver. This works also quite well. And then there's another idea my colleagues have done in, let me go to the relevant page here. So in this paper, what they have done is they trained the receiver for a maximum constellation size. I think it's 256. And And then when you essentially just send 16 QAM, you mask essentially some of the output bits because they are not needed. So this actually means that it's actually possible to have a single neural receiver that can adapt to different constellation sizes quite nicely.
Thank you so much. I think it is clear now. There are some questions around the real-time processing aspect, which even I had in my mind while we were talking, because we talked about symbol-wise processing, block-wise processing, and you moved on to other schemes also. So how are these to be done? How real-time, and also whether what kind of processing are we talking about? And then another question is similarly about the variations in the channel. I think you touched upon this aspect, but the question is about mobility, whether mobility will increase the complexity of the prediction, or could you comment on these two aspects?
Okay, let me start with the mobility. That's the easier one. So, for example, what we have done, first of all, in this paper that's referenced on this slide, but also in this end-to-end paper here, what we have done, for example, we trained this constellation has been optimized for many different channel models, but also many different Doppler spreads. So ranging from 0 until 130 kilometers per hour. And this is a single constellation, for example, that has been optimized for all of these scenarios. And meaning you can essentially use this across essentially all conditions, and you get the same benefits of not requiring any pilots anymore. So it means the price to pay is that you need to train for much longer for much longer time. And also you become less specific. So this means the more fine-grained you would like to adapt to channel conditions. So for example, you could think about, can I train a system that only works for high-speed users and other for walking speed users, etc. Yes, you can do this. Then you have the additional complexity related to managing multiple models for different conditions. And so I hope this answers the first part of the question. And now there was the second part was related to about what type of processing we are talking about. And I mean, we are talking about processing at physical layer speeds. So this is in the order of nano to microsecond inference speed, which is extremely fast. So it's orders of magnitude faster than what's, for example, required for the autonomous car industry. And so the downside is that actually the available hardware accelerators that there are, I'm just trying to find the corresponding slides, they are not targeted towards L1 kind of loads. And so I think there's a need for having communications specific hardware accelerators, which are jointly kind of developed with the corresponding algorithms. So I think it's very important for us actually to bring hardware and algorithm together to come up with the most efficient implementation.
Very interesting. Yep. I think we are covering most of the types of questions according to my classification of what is coming in. There is one question which is quite interesting about simulations. So what kind of data generation are we talking about here? Is that something which can be simulated? Of course, in the ITU problem statement, we used simulator to generate the data, but I want to ask you, in this type of schemes, you mentioned about that the model training which the colleagues have done. What is the type of data are we talking about? What type of simulators, if at all, are we talking about? And what kind of training? Is it offline? Is it online? What kind of training are we talking about?
Okay, yeah, very good question and big pain point. So I think that most research is purely based on simulations. And for example, what I've done here and all the papers I've referenced, they all use simulated data, essentially using the 3GPP models to generate channel time impulse responses. And so this means that's only, yeah, I don't know what that's really was, but I think it's the first indication that these things seem to work quite well. And it also allows us to train quite quickly over a very large kind of variety of setups. Now, I think many companies, also Nokia included, we have, of course, access to real data from our products, but this is not something which is openly shared with the academic community. And but although that's possible, there's one difficulty related to these are not things that you can generate in a lab. So for example, if you would like to get access to received kind of OFDM grids for a user moving at 130 kilometers per hour, you would actually need to have a base station close to a highway and then be able to extract the physical layer data from a commercial product. And so that's actually something I would almost believe hardly any company in the world can do and make essentially this type of data available to researchers. But this is, I think, what's needed. So there's right now, I think, a huge discussion going on about how can we actually make physical layer data easily available to from commercial products, but also how this data could be shared, for example, into open data sets in a way that one wouldn't reveal too much about the implementation of the products. So that's a big pain point. But I also think that going towards real measured data is actually the only way to move forward in the future. And I also expect that we will see even further performance gains than what we see in simulations because of many things that we are ignoring. For example, here in my simulations, I have ignored all type of transceiver impairments, non-linearities that haven't been modeled. Also the channel model, for example, that I've used here, ignores totally that subcarriers might become not orthogonal anymore due to the high Doppler. So many things which are over idealistic and need to be accounted for. So, so I think it's a challenge for our community. Actually, how can we make relevant data sets available to a large community?
And just one last question, the real-time aspect of it, is it really important to have the data real-time, or is it okay to have offline data for this kind of simulations?
So I think you can do it totally offline. So okay. You can. I actually think if you're able to generate a huge data set, you can get away with offline training somewhere in a lab. So I don't believe that for these type of applications, you would really need to do real-time online adaptation and training. I think that's not practical. And I also think that nobody would really like to put kind of training capabilities inside the SOC sitting in a in a distributed unit of a 5G system. So I think it seems far more pragmatic to me to try to go as far as we can with offline training.
Understood. Yes, I think we are covering most of what we wanted to discuss. We are out of time, unfortunately. A very good discussion. Thank you so much for staying back and very patiently answering all these questions. Thank you for your excellent presentation. For those answers, it is quite exciting research. We look forward to seeing more output from you and your colleagues. Thank you so much. Over to you, Thomas.
Okay. Yeah, that's great pleasure. And thanks also to the audience for the good discussions. And if anyone wants to reach out, I'm happy to continue the discussions through email or other channels if needed. So thanks.
Thank you so much, Vishnu, for taking care of the Q&A session. And A very big appreciation to Jacob for the wonderful talk titled The Road Towards AI Native Interface for 6G.